Can you guys hear me? I think we'll wait a bit, 10, 20 seconds. Can you guys hear me? Any those people attending? So please, if you hear me and you're attending, please just say yes. It's gonna take a while to. Awesome. Okay, so let's review a bit of group actions. Okay. Group actions. So this would be a group. And it's G set. Should I remind you of the definition of a group action, or that's
Yes,
yes. So I have from G cross S to S that sends a pair GS to an element that we call G star S, such that G star S is equal to S for all S in S, for all S in S, and G1 star G2 star S is equal to G1 G2 star S for all G1, G2, and G, and S. Okay, these are the definitions of a group. Okay. Now let's give an example of a group action. Let G be a group. Okay, I assume that you're familiar with orbits and stabilizer and things like that. Okay, let's, unless you want me to go through it quickly, but here is, you can read your notes for that. We just do some practice. So this is a group action. Now, one important group action is a group, and G acts on itself by conjugation. You remember this? You have a function from G cross G to G that sends G and X, okay, Gx, G and G and X and G to Gx G inverse, right? G is in G and X is in G. Okay, this is a conjugation action. We've checked many times that this is a group action, right? You remember that? We've checked this many times. Okay. So far, so good. Okay. Yeah, any general questions on these? Like, we all know how to check group action. We all know how to check that an action is actually a group. Okay. Well, a operation from, or a function from G times S to S is a group action. Okay. So I'll move on to study, well, to look at the solutions of the bonus homework that I have posted. So I will I'll solve these questions, the ones that you had during the bonus homework. So exercise, let G be a group, and H a normal subgroup of G. Show that G acts on H by conjugation, and that the set fixed points of this action is H intersection that G. What are the fixed point of an action? What is a fixed point? It's a point that doesn't change when I hit it with G, right? G star S is equal to S for all G and G. That's a fixed point, right? S is a fixed point if and only if G star S is equal to S for all G and G. This is the definition. What else can I say? Fixed point are correspond to what type of orbits? To singleton orbits. That's very good. Okay. Well, a point or an element S0 and S is called the fixed point. If and only if G star S0 is equal to S0 for all G and G, and if and only if the orbit of S0 is actually S0, right? You remember this? All of these are equivalent definitions of fixed points. Are we good here? Yeah, we remember this? Okay, so let's prove this claim. Let G be a group and H an almost subgroup of G. Show that G acts on H by conjugation, and that the set of fixed points of this action is H intersection ZG. Now, so let G be in G and H be in H. First of all, I have to show that G inverse belongs to H. Why is that true? I have to justify why I have a function from G cross H to H that sends G and H to G inverse. Now I have to show why this element is in H. Why is this element in H? Yeah,
Because H is normal.
H is normal. Since H is normal in G inverse belongs to H. So if you take any G in G and any H in H, G inverse belongs to H. Okay? Now what do I have to show? I'm going to call this T star H. Oh, it's better to write T star H, G H. Okay, are we good here? It's very important that the function goes from G times H to H. If H weren't normal, I wouldn't be able to say this. I wouldn't be able to say that G acts on H. So far, so good? I wouldn't be able to say that G acts on H by conjugation. Is it clear? Any questions? Any questions so far? Is it clear? Okay. Now let's prove that star is a group action. Let's prove star is an action. I need to show the two definitions, right? So let H be H. What is EG star H? EG star H is just EG, H, EG inverse. What is that? What is that, everyone?
H.
Sorry. Yeah, should be clear, right? H. Now let G1, G2 be in G, and H be in H. What is G1 star G2 star H? This is G1 star G2 H, G2 inverse, which is just G1 G2 H, G2 inverse, G1 inverse. What is that? So G1 star. Let me rewrite this here. I can just write this down this way. G1, G2, G1 inverse. So what is that? This is just G1, G2. So far, so good? Okay. Are we good? So star defines a group action. Clear? Any questions, please let me know. I want to raise here. Okay, I'll keep it. Yes.
How would you recommend to like the
Practice.
okay so look at a question, I already know it's stop. So.
Yeah, no, it's not an easy. It's not easy. So you just look at the definition. Every question you could practice it.
The answer.
Yeah, exactly. I mean, first of all, try without looking at the answer. Try it. If you can't, try it. If you can't, ask someone to help you out. If you really can't, look at the answer. Okay. Okay. Is it clear? I mean, I'm always here if anyone, there's someone is okay, you can always ask. Okay, so but the key is to try it. These are a lot of this is just checking definitions. Showing something is an action, it's usually checking definitions. Okay, great. So far so good. Now what I'll erase this one. Should I erase it? Can I erase here? Yeah. Okay, so what is a set of fixed points? A fixed point is an element in H, right? Because the G set here, what is a G set? G is acting on a set. What is the set? H, right? So H and H is a fixed point. If and only if what? If and only if G star H is equal to H for all G and G. So far, so good. Yes? What is G star H? GH, G inverse, very good. Is equal to H for all G and G. Well, what can you do here? Someone else? What can you do here? What can you do? If I want to show that H belongs to ZG, I multiply by G on the side there. Very good. And only if GH is equal to HG for all G, if and only if H belongs to ZG. And that does it, right? Hence the set of fixed point is what is the set of fixed points? It's H intersection G, intersection ZG. You agree with this, everybody? You see that? H belongs to H is a fixed point, if and only if it belongs to ZG. Is H intersection ZG. So far, so good. Any questions on this? Is it clear? Please ask. Don't hesitate to ask. Okay. Great. Are we good? Yeah. Okay. Now I'll do one more question. I'll do two more questions actually that were on this homework, and then I'll do the third one. I'll do one, and then I'll do another one, and then do an application of the other one. Okay. Now another question that we did in class, but I'll do it a different way. It should be a finite group. And H a subgroup of G of index P, where P is the smallest, what did I say? Where P is the smallest prime divisor. Did I just say this? Where P is the smallest prime divisor of G, right? You said divide. Where P is the smallest divisor of G that is bigger than 1. Yeah, that's what I said. Okay. Where P is the smallest non-trivial, let's say. Trivial, non-trivial means bigger than trivial divisor. Prove that H is normal in G. Okay, so in class I did this with the coset representation. If you remember this, right? In class I did this with coset representation. Yeah. So in class, I will do it another way. Class, we've done that using coset representation. Now we'll do it another way. I think many of you have seen this last week. We'll do it another way. It's a bit more elementary, but very nice. Okay. It's we'll come up with a group action that will lead us to show that H is normal. Okay, so proof. Now in class, if you remember the proof of the second Taylor theorem, we'll have a subgroup act on the space of coset, if you remember this proof. Now we'll kind of do the same thing here. So we'll just say let H on G modulo H, the space of left cosets. Right? G modulo H is not necessarily a group. G modulo H is just the space of left cosets. Now, how do I let this act? There's the natural act, well, the action that is obvious, I guess. The H star XH to just H XH. Here H is in H and X is in G. And I let it act this way. Okay? H will act on G mod H. You just take an H in H and a left coset of H. And how do you let this act? Instead of letting H be in G, you just restrict them to be in H. Right? Just say it's Hx times H. This is a group action. We've proved this, right? If you remember. We proved this in the lecture, so this is a group action. Star is a group action. And I think we call it the restriction of the action of G to H. Did we call it this way? Did we call it this way? Okay. I mean, you're looking at G acting on G mod H, and you just restrict it to H. You don't want the full G acting, you just look at H act. I mean, H is a group in its own right, so, right? You agree that H is a group. So H could act on G mod H, and H is a subgroup of G. H is a subset of G, so you can still multiply X and H. This is a product in G. Nothing wrong in here. So far, so good? Any questions? We're good? Yeah.
How did you know?
Yeah. How do you know? It's a practice. Okay, it's practice. Yes. If this X is in H, because this X is in G, not in H. X is in G, right? These are the space of left cosets. What are these? They're just XH or XH, and X is in G. But let's now use your remark. What is the orbit of H? H is a coset, right? What is the orbit of H? So really you put X equal to the identity here, right? If you put X equal to the identity, or X, any X belonging in H, you just get that this is H times H as H is in H. What is this? H, right? Agreed? So for this coset H, for the particular coset identity times H, which is H, the action is trivial, right? The action doesn't change it. So H is a fixed point. H is a fixed point. This action. Okay? Yeah.
Yeah, sorry, I just forgot. Wouldn't prove that H triangle G?
H is a normal subgroup of G. This is a normal subgroup. H Okay, I've used this notation before. I think I did. Yeah. Okay, so H is a fixed point of this action. We agree with this? Everybody, do we agree with this? Yeah. Why? Oh, I'm taking the orbit of the coset H. So how many left coset do you have? Let's call them H, H2H, until HPH, right? I'm asking you to look at the orbit of this one. What is the orbit of this one? It's just H. Yeah.
Normal then H X H equal H.
Yes, exactly. Well, yeah, that's it. But I want to show that H is normal. Right? I want to show that H is normal. But I'll get back to your point. I'll get back to it. So H is a fixed point. So if H is normal, parentheses. Suppose that I knew that H is normal. All of these orbits would have size 1. But we'll get back to this later. Okay? Well, I'll get back to this later. Now H is a fixed point of this action. Agreed? Now, what is the size of G mod H? Let me erase this. But I mean, you agree with this? No, sorry, it's not H. It's X2, XB. It doesn't matter. Where? Okay, I'll just erase because I don't have space to write this. I don't have space. Okay. Now, let's pick an S and G mod H that is different than H. That's not equal to H. Okay. Pick an S that is not equal to H. What can you say about the orbit of S? Let me write this down here. Can I erase this statement? Can I erase that? Yeah. What can you say about the size of the orbit of S? What do we know about two orbits? They're either disjoint or equal. Okay, so so maybe I'll just do this picture. Let's rewrite this out. I have G mod H is equal to H, H2H, oh man, X2H, XPH, where X1 is equal to EG, X2, XP are representatives of the P left cosets of H. Okay, H has how many left cosets? P, right? The index of H is P left. Okay. Of the distinct P left cosets of each of them. Okay. Now, what is the orbit of H? Orbit of H is what? H. So H lies in its own bubble, right? Lies in its own orbit. Agree? Now take any S different than H. If S is different than H, if S is different than H, what do I know about two orbits? They're either equal or disjoint. So can H belong to the orbit of S? If S is different than H, since you don't have to read it detailed, I understand that But since two orbits are disjoint or equal, then H does not belong to orb S. Agreed? So what can I say about the size of orbit of S? At most, what is it? So H doesn't belong to the orbit of S. What can I say about the size of the orbit of S? I know it's less or equal to P because it's a subset of G mod H, right? But can I do a better? Can I give a better estimate if I know that H doesn't belong to that orbit? P minus 1. P minus 1. So orbit S is less or equal to P minus 1. Great. So far, so good. Any questions here? Let's repeat that. I have that H is its own orbit, right? So H doesn't intersect any other orbit except itself. Now, if you pick S that is different than H, the orbit of S will not contain H. So this means that the orbit of S has size at most P minus 1. Now, what do I know about the orbit stabilizer? The size of orbit of S is equal to H stab S. Agree or not? Yes? Orbit stabilizer. And this one divides the size of H. Right? Because H is equal to H stab S times stab S. Right? Agree so far? Yeah? So what is H? H is index of stab S times stab S, right? Now, orb of S is this one. And this one is a factor of H. So orbit of S will divide H. Agree? Yes. So the orbit of S will divide G, divides G, divides the size of G, since H divides G by Lagrange. So far, so good. Great. Now, orbit of S be that orbit of S is less or equal than P minus 1. And orbit of S, the size of orbit of S divides G. Now read the hypothesis. What do I know about the divisors of G? What is the smallest divisor of G that is bigger than 1? P. This is less or equal than P minus 1. And it divides G. And I know that P is the smallest divisor of G that is bigger than 1. So what is the size of orbit? Exactly. P is the smallest non-trivial divisor of G. So what? So orb S is 1. Agree? So orb S is equal to S. Orb S is equal to S. So far, so good. Yes? Well, okay, so all the orbits of this action, what can I say about them? Every point is a fixed point, right? Because all the orbits are singleton. The orbit of H is a singleton, and the orbit of an element different than H is a singleton. Hence, every element of G mod H is a fixed point. Is a fixed point of H, okay? Just to emphasize that it's H that is acting and not G. Okay, I'm just emphasizing that it's H that is acting and not G. Okay, now, well, let x be in G. Well, let x be in G, and H be in H. Since any orbit is a fixed point, what can I say about H star XH? Is equal to XH. Right. We agree or not? XH is an element of S. And every element of S is a fixed point. So H star XH is equal to XH. So far, so good. Well, what do I get here? I get HXH is equal to XH. What do you do now? Someone else?
Bring X over Y.
So X inverse XH is equal to 8. What can I say about X inverse X? Well, what can I say about X inverse HX? It belongs to me. Right. X inverse HX. Okay. Now H and X were arbitrary, right? So X and G, X and H were X and G, and H and H were arbitrary. So H is normal in G. Yes.
Could we have made like an argument by doing like the number of fixed points from the beginning? Like we found that like H was a fixed point, and then we could argue about the like number of fixed points. And since we know that P is the minimal prime number, we would get that every point is a fixed point.
I mean, this is the proof of it. I just proved it here. Right?
Yeah.
You have to prove it, right? Because this is not a P group. When a P
Yeah.
group is acting, you have a theorem. In general, I mean, you can make a theorem. So say, I don't know, if, so basically we can make a small proposition, I guess, from let G be a group and S is set, a finite set. A finite set, let G be a finite group, and S a finite set of size P, right? Where P is the smallest non-trivial divisor. I mean, the smallest non-trivial divisor is always a prime number. Right? Now, if there exists a fixed point, then all the other elements are fixed points.
Yeah.
Right? So if G has one fixed point, let's say, I mean, the proof, I will prove it here, right? G has one fixed point in S, and every point in S is at the same. Okay, it's the same argument. Right? You have a fixed point. Now you take any element different than S0 as a non-fixed point in S. Then you take any element different than that fixed point, and you show it orbit must have size 1. Okay, it's the same argument. But I don't want you to make up your theorems. Okay, just if it's something in class, for P groups, we have seen that the size of the set is congruent to the number of fixed point one. Okay, so here you get it. But in lesser is that. So really what I proved here, we proved something. I mean, I'll get back to someone, you have a good reading. Pro. Now we proved something here that maybe I'll get back. So basically, suppose that H acts on G mod H. Here we prove that if all the actions have, if all the orbits are, if all the points are fixed points, then H is normal in G. Right? That's what we proved here. If all the points are fixed points, then H is normal in G. and the converse also holds. Suppose that H is normal in G. If H is normal in G, then H star XH. What is that equal to? This is just H XH, right? Is that equal to XH or not?
Yeah.
XH? Is it equal to XH? If H is normal in G, is that equal to XH? If you want to convince yourself, try to bring that X inverse HX the other side, and that will be equal. Or HX. Now X inverse HX will belong to H. Agree? So X inverse HX times H is equal to H. Multiplied by X on the left. Well, multiplied by X on the left, yeah. Basically, H is normal if and only if the action of H on G mod H is a trivial action. Basically, every point is fixed. Okay? You guys see that? Was that what you wanted? No? Yeah. But yeah, so if we proved here that if all the points are fixed, then H is normal, right? Now, if H is normal, then all the points are fixed. The same time. Okay. I mean, anyways, that's not worried about that much. Or it's a good exercise. Try it out. Yeah.
Can you help with the intuition for coming up with group action?
The intuition is practice. Okay. See as many group actions as you can and hope that one of them works. Okay, at least for now. Okay. So it's practice. Yes.
I say field harder than ring.
I mean that has nothing to do with what
No, I know, sorry, it's getting around it.
okay.
Yeah, I mean,
I prefer the big cube.
and does that say G is a H is left coset of G, or is that G divided G is a G mod H?
Where?
G slash H.
This is the set of left cosets.
Okay, yeah.
Okay. Are we good here? Okay. Now I'll do one more question and then apply it, and then we move on to coset representations. I don't know if we have that. I mean, I have the room on delayed, so I can't stay on delayed, but if you guys want to see? Yeah, sure.
I don't stay that late anymore.
I don't.
Go outside.
Yeah, I mean, okay. So let's. Do we still have people? Yeah, we still have people. Also, for the final, is it worth to do problems from the book, or should we focus? I mean, let's talk about this now. Then we'll worry about the final afterwards. Okay. Now we'll do a question, and then I will do an application of this question. Okay, it's a question that was on your homework. Let me be a finite group. We didn't have finite, but let's just make this assumption now. And H a subgroup of G. Show that G acts on the set S XH X inverse as X is in G by conjugation. Basically, H S. So I take G and an element XH X inverse, and I send it to G star, to G star XH X inverse, which is defined to be as GX H X inverse. Okay, sorry if you can't see that, but that's the action, right? Should I rewrite this upstairs? Yeah, let me do that. G X X inverse equals to G star XH X inverse, which I define it to be the XH X inverse. Okay, should I show it's an action or it's good? It's good. You've shown it's an action. Should I show it? Should I show it's an action or are we good? We're good? Okay.
What's the question?
Oh, yeah, yeah. So G acts transitively on S. And deduce. This is the new part. This you've done this, right? This you've done in the homework. And deduce that if H has index and strictly bigger than 1, then G is different than the union. Pretty weird. Well, not very weird, but pretty nice result. We can do it with group actions. And then we can generalize it here. I assume that G is finite. Then maybe I posted already your last homework, so I can't edit it. Unless you want me to edit it, then was one more question. Other than that. Okay. It's an interesting question. Okay, so proving it's a group action is okay, I guess. Everybody should I do it? You want me to do it? Okay. If you want me to do it, please let me know. Can do that. I mean, what is clear is that you take an element G star XH X inverse, you get back an element in S. You agree with this? Yeah? Yeah. So I mean, should I prove? I'll prove it's a group action. I mean, EG star XH X inverse is equal to EG X inverse EG inverse. You just XH X inverse here. Let X be T. And what as well? So let G1, G2 be G, and X be G. G1 star G2 star XH X inverse. So just G1 star G2 X inverse G2 inverse. This is just G1 G2 X inverse G2 inverse and G1 inverse. This is just, I mean, you can write G2 inverse as G1 inverse as G1 G2 inverse, right? Let me write this once more. Okay. Yeah, and this is just G1, G2 star. Excellent. Okay, so this is a group action. Are we good? Yeah? All good? Now I will prove it's a transitive action. What does transitive mean?
There's only one orbit, or you could say that you could go from any one like element to the other.
Exactly. Or the orbit of one element is the whole set, right? The orbit of an element S in the set is the entire set. Okay, so let's look at that because orbit is being in the same orbit is an equivalence relation. So if you prove that the orbit of one element is the whole set, then you're done, right? Okay, so what is the orbit of H? The orbit of H, I think I did this one in class, right? This is just G star H as G is in G. Agree or not? Yes? What is that? This is just G H G inverse. And G is in G. Agree or not? What is this? It's just X. It's just my set S. Instead of indexing it by X, I index it by G. Okay? So G acts transitively on S. Did you guys write this down? Can I move? Yeah. So G acts transitively on S. Okay. I mean, I didn't write the part, but what's the stabilizer of H? What is step H? This is the set G and G, such that G star H is equal to H. Agree or not? By definition. Now this is just E and G, such that GH E inverse is equal to H. It's normalizer of H and G. You remember that? Yeah? Remember this? It's NGH. We call it the normalizer. And this gives you another proof that the normalizer is a subgroup. Right? Why is that? Because you can express it as a stabilizer of a point with respect to an action. The stabilizer is always a subgroup. Okay? Is that clear? Now, I want to show that H is a subgroup of NGH. Is H an element of, is H contained in NGH? So can you put H if H is an H? I mean, you know, H is a normal subgroup of NGH. You can see that by definition. But anyways, can you see that H is a normal subgroup of NGH? H is a normal NGH. Not only is H a subgroup of NGH, but H is a normal subgroup of NGH. Can you guys see that or not? So, I mean, H is a subgroup of NGH. Why is that? If H belongs to H, then what is H? H inverse. It's H. So H belongs to NGH. Okay. Are we good? Yes.
Is that enough? Like if you have,
I just have subgroup. I don't want to say so. I don't want to show.
yeah, yeah, but that's enough to show it's a subgroup. Like
Yeah.
it's a group and it's contained, so it's
Yeah.
a subgroup.
What's a subgroup? It's a group in its own right.
Yeah, but like you don't have to go through all the.
No, because you know already that
Yeah,
says it. The operations are inherited from G.
Yeah.
Right. You know that H is closed under addition under the group law. H contains the identity and H contains the inverse.
Yeah, because it's like it's a group. It's contained in.
Exactly. H is a subgroup of G. It's contained in the other subgroup of G. So H is a subgroup of it. Yeah. Okay. Now, I mean, I'll leave it to you to check why H is a normal subgroup of NGH. Okay, that shouldn't be bad. Is that clear why H is a normal subgroup of NGH?
Isn't this a homework?
I don't know. I don't know if I put it as a did I put it as a homework?
I feel like I see it somewhere.
It was on the bonus.
Because on the bonus was H is a subgroup of NGH.
Yeah.
Not normal.
I think it's yeah. It says that H is a subgroup of NGH.
Yeah, but you can show that H is a normal subgroup of NGH. But I mean, you can try that. Okay, try that. Yes. NGH is not necessarily normal, but NGH is the largest subgroup of G in which H is normal. Technically, if you can invert it this way. GH is equal to HG for all G in NGH.
So NG.
Not necessarily. You need G NGH is equal to NGH times G, not H. Right? So I mean, you know, to prove, so let X be in NGH. I have that X inverse is equal to H. Right? So H is a normal subgroup of NGH. So H is normal in NGH. Okay. NGH is not necessarily normal. but you know that H is a normal subgroup. Okay. Okay, great. Now I need to show that G is different than the union of the conjugates of H if H has index M strictly bigger than M. Now, and then if G is finite, if G is finite, the index by the orbit stabilizer, the index of NGH is equal to the cardinality of S. Agree or not? The index of the stabilizer is equal to the size of the orbit of H, right? And what is the orbit of H? It's the entire S. Agree or not? Yes? So this is the size of S. Okay. Now suppose G, the index of H and G is N strictly bigger than 1. How could I show that G is not the union of the conjugates of H? So first of all, can you compare these two things? Can you compare G and GH and GH? So you know that H is a subgroup of NGH, is a subgroup of G. Yes.
So then you can use like you could say the index of H and G is equal to the index of H and NG and the index of NG.
Very good, thank you. We agree with this? So really, the index of NGH is less or equal than the index of H. In fact, it divides it, right? This also holds for infinite groups as long as the indices are finite. But anyways, let's not worry about that. Agree or not, this is just, I mean, I can say it divides it, but I don't need the full power of dividing. Agree so far? Yes.
Can we also just say that because H is a subgroup of NGH?
Yeah, sure. You can say that, yeah. H has subgroup NGH.
So the index
So exactly.
greater or equal.
Yeah, because I mean here you're using that G is finite, right?
Yeah.
But it also holds in infinite cases, as long as the index of H is. Okay, so far so good here. Now what is this? The cardinality of S, which is equal to G and GH, the index of NGH, is less or equal to M. Right? Have a look at the cardinality of S. It's the index of NGH. So it's less or equal to M. Okay. Now to show that G is different, let's just count. Let's count. Or let's bounce. Let's count. So if I manage to show that this union has strictly less elements than G, then I'm done. Isn't that right? If I show that, suppose G has 15 elements. If I show that this has strictly less than 15 elements, then I'm done. Agree with this? Okay, now how did I do that? I claim that there is a common element to all of these elements in the union. What's the common element? Agree? All of these G A G inverse are subgroups of G. So there is one common element, which is the identity. At least one common element. Are we good? So e.g. is a common element to G H G inverse of G.
So then you can say that the union is strictly smaller than the sum. Or do you have to do like-
Well, you have to remove one.
yeah, it's
Exactly.
Yeah.
So very good, very good. Yeah. This is the idea.
so like you compare it to the sum and you will have to remove identity because it's like you if you just did the sum you would repeat it because it's common.
Exactly. Exactly. So how many new elements do I have? At most. Now at most. I have the identity, right? As I have the identity. Agree or not? Okay. Now you agree that GHG inverse has the same size as G, has the same size as H, right? All of these are finite because G is finite, right? We agree with this. Should we draw a picture? Can we draw a picture? Is it better if I draw a picture? Let's draw a picture with the worst case scenario where there is actually the identity is the common element, is the only common element. So what do you have here? This is H. This is GH, G inverse. G1H, G1 inverse. And this is another one, G2H, G2 inverse. And this is the identity. Okay? Worst case scenario, only the identity is common to any two of them. So you have one element here. How many remaining elements do you have here? Size of H minus 1. We agree? All of these have the same size. So far, so good. I say that the identity is common. So at most, how many distinct elements you have? H minus 1. Agree or not? Agree or not? 1. We're not done. So everyone has at most a contribution of H minus 1 distinct elements. At most. Are we good here? Yeah. Okay, now how many of these H's you have? How many of these conjugates you have? At most. At most you have S of them, right? Now you don't know what S is, but you know you can bound S by above by M. Okay. Plus M. So far so good or not? Do you want me to repeat this? Okay. So how many distinct elements you have at most? You have one that is common to all of them. Now at most, all of the remaining ones are different than each other. So you have H minus 1 new elements. Here you have H minus 1 new elements. Here you have H minus 1 new elements. H minus 1, H minus 1. Now, so every group will bring, every conjugate of H will bring at most H minus 1 distinct elements. Right? How many distinct conjugates you have? At most, M. So at most you have this many elements. Yeah.
But then once you like
Yeah, you're just want to, yeah, before I move on. Is it good? Yes. Conjugation by G is an isomorphism from G to G, right? I from G to G that sends X to G, X, G inverse is an isomorphism, right? So phi of h, will be isomorphic to h. In particular, if they're finite, they will have the same size. Are we good? Yeah. Are we good with this? Are we good? Okay. Yeah. So counting is good here. Yes, please.
Oh yeah. So once you develop like the M,
Mm-hmm.
like you distribute it, you
Yeah.
get M times size of H, which is size of G, and then you do minus M. But since M is strictly greater than 1, this is strictly smaller than size of G.
Exactly. Very good. Are we good here or not? Is this good? Is this part okay? Everybody, is this part okay? Okay. Let's expand that. Okay. So at most UG elements. Now let's look at one. What do I have here? H minus 1. What is that? This is just 1 plus M times H minus M. Agree or not? Now, what is M? Look at M. What is the definition of M? It's the index of H. This is 1 plus G index H times the size of H minus M. What is the index of H times the size of H? It's equal to the size of G. So I have here, this is just the size of G plus 1 minus M. Now I have that M is bigger than 1. So this number here is strictly group actions in action. You know, it's you can see that it's very, very powerful tool. Is it clear? Okay, so let's write this out. I mean, you can generalize this. I mean, maybe I'll post it as an exercise, not to be graded, but maybe I'll put it on your practice final or something. I mean, it's a too hard exercise. It's not an essay.
You're gonna give us practice finals?
Pardon me?
You're gonna give us practice?
Yeah, I'll give you a practice final, but again, don't rely on it. It's not like, don't just it can give you an idea of the level. Okay, and it's just for the formats. Yeah, definitely. Assignments or notes are way more important than a practice final that I would write in like 10 seconds. Like,
So you
okay, I'll
said,
write 10 minutes, put in some questions. The notes are way important than practice. Yes.
you're also saying that for assignment, like the last assignment, like
Yes.
the question on groups are gonna be similar hardness to.
Yes. Yes, they're going to be some questions are going to be of similar difficulty. Yeah. No, 6 on group, 6 are on rings. They're not. I don't think they should. They're. It should make you think.
But
Yeah.
is it like so?
How do you know?
Because
Sorry. Yeah.
it says that the level of the questions of the groups, like the first 6 questions,
Yeah.
it's like what we should expect for the final.
No. I'm saying the same level. The same level of thinking because
Yeah, I'm
CLO theories are not covered on the final except on the 2 and 3.
Yeah, I'm just talking about the level.
Yes. Yeah.
So we should expect this kind of.
Not on every single question. Right.
Oh, okay. So
Not on
it's
every
like,
single question.
okay,
Okay.
so it's like
So-
that's what we put in.
I would say so. Again, it's a bias of it because I'm the one who wrote it. Like it's a.
So you said we only need Silo theorem, we only know the proof of 2 and 3,
And the statement of the truth.
and the statement, and not the proof of the last 2.
The last 2. I mean, the last. Okay, so but just please look at this one. I'll do this one. So G. Different than union D. What time is it? 7:07. If you guys want, we can do some coset representation, or we can just leave. I don't mind. If you want, we can do coset. We can do coset representation. I could stay. Yes.
Is the question also?
Oh yes. Yes. Okay. I'll just do some coset representations and then move to the question. Oh, okay. Don't know what happened. Okay, great. Okay, is that clear? Okay, so I'll do some coset representations, like the action of G on this coset. But yeah, for the final, again, I mean, I said in class 7 questions. one proof will be from groups. So the first three questions are proof from the notes. That doesn't mean other questions will not contain proofs from the notes. But these are three questions. So each question is on 10 marks. And some questions should be easy. Usually the first few questions, I guess, are from the notes. And as you see, they're all, you should be able to get it. Okay, you should be able, every question from the notes, you should be able to get it. Because I've done it in class. Okay, so you should, these are proof of things from the notes. Two will be on rings and fields, and the chapter from rings, and one will be from the chapter of rings. Those are supposed to be, I hope at least everybody will get them. Okay, then other questions, I will still put things from the notes, and I can still put things from the assignment and mix it up with some new things. Okay, so again, the key is the notes and the homework. This is the key. Know very well your notes. Make sure you master your homework, and then it's a safe bet. That's what I would say. Okay, yeah.
Is it worth it?
The notes and the homework is better. Okay. Yeah.
So you're saying for like final, we know 4 on groups, 3 on rings.
Yeah.
And then from the 3 on rings, there's 2 of them is proof.
Two proofs on the notes.
2 proof on the note.
Yeah, and one will be calculation.
Yeah, oh yeah, that's what you said. And for the group part, one is gonna be proof from the note.
Yes.
And then the other 3 unknown.
The other 3, I mean, you can look at the homework. You can still get something from the notes, right? A calculation from the notes, something like that. Okay, but I mean, all the questions are worth 10 marks. Now the proof is going to be worth 10 marks. It might be a proof of 2-3 lines, or it might be a big proof. Okay, but again, so focus on homework and notes. That's what I would do. Just focus on the homework and the notes. Make sure to know every single theorem. Make sure to know how to do every single exercise in the homework. Right? Like even in the practice, in the last final that I have, not the last final, the last homework that I have. Make sure you know to do well. I mean, there is going to be some silo stuff, but a lot of it is going to be group action. A lot of it is going to be coset representations. So make sure to know how to do these. If you know how to do these, you know how to do calculations. You know how to do you know how to compute elements of the dihedral group on the square. If you know these, then you should be fine. Yeah, and I mean, yeah, I said that doesn't really narrow it, but yes.
Just a question about the homework 9.
Yeah.
Are like their questions on the rings?
Yeah.
We'll cover the material for them, like
by Friday.
By Friday.
By Friday, or a bit by Monday. But the question on the rings, I'm not really worried about. The question on the rings, I think there's only one question that is long.
Because it's due on the Tuesday.
On Tuesday, yeah. So the question on rings are not long. The question on rings should be, many of them should be 1 or 2 lines.
That's only 3 or 4.
There's only?
No.
No, I think it's 6 and 6.
Oh, yeah.
6 and 6. 6 and 6. Yeah, so the question on rings, I think are going to be easy to do. Most of them are going to be easy. Okay, but the groups one are a bit tougher.
Yes.
Yeah, the groups are a bit tougher. But anyways, that's again, this is the level you should expect for some questions. Okay, and again, I think I give you hints on it, like do that and do that.
Yes.
If you follow the hints, should be fairly well. I won't say easy, but it should. If you follow the hints, usually it will guide you to the right answer. Okay, in a quick way. Maybe you can find a quicker way than that. Very happy to see it, but the hint will guide you to a very quick way. Okay, now let's look at the coset representation. By the way, when do you guys want a review session? Do you want it? I mean, I'm thinking of holding 2 or 3, just because there's a lot of material. And then it's gonna be like the previous one. Just gonna tell you the important theorems, the important things in the homework. Definitely, that's not an exhaustive list, but just the main ideas. You prefer it like starting next week, or like all of them like 1 week before the final?
Starting
Starting next week. Okay. Yeah. Yeah. I'll record this because it's very difficult to find a room for 200 people. outside of plus hours. Yeah, so I'll read. Yeah. Okay, so now let's move on to some exercises on coset representation. Okay, so first let's start with some background. Let's repeat some background material. Let G be a group. In S in B set. They have an action of G on S that sends a pair GS to G star S. This is G is in G. S is in S. Then the action of G on S induces a homomorphism I think I call it rho. Usually I call it rho. Rho. Rho is a bad name. Rho should be used for something else, but that's okay. Rho from G to sim S. That sends an element G to the function lambda G, where lambda G from S to S sends little s to G star S. Right? In class, we proved that lambda G is a bijection. We proved that lambda G is a sequence. Remember this? We wrote an inverse for it. Lambda G inverse is an inverse for lambda G. And by the proposition or by the properties of group actions, lambda G and lambda G inverses were inverse functions of each other. Okay, remember this? Everybody remember this? Yes or no? Yeah.
Certain science.
How is it fair? Okay, so lambda G is a function from S to S. You agree? You send S to G star S. So you're fixing G, and any S, you hit it by G. So you get a function from S to S. Not only is this a function, but it's a bijective function. Okay, should I prove why it's a bijective function? No, is it clear? Okay, I mean I could write it down. What is lambda G inverse composed with lambda G of S? This is just G inverse star G star S, and just G inverse G star S, which is just S. Okay, and the same thing, lambda G composed with lambda G inverse, so lambda G inverse composed with lambda G is identity on S, and similarly, lambda G composed with lambda G inverse is identity on S. Similar way, or just flip G and G inverse. Okay, because G is G inverse inverse. Anyways, you can see that. Is that clear? Yeah. Okay, so this is a symmetry. This is a bijective function from G to G, from S to S. Okay. Now send this G to that particular function lambda G, and you get its homomorphism. Is it clear? Should I prove its homomorphism? Should I prove its homomorphism? Yeah, I can prove that. Sure. So, what is rho of G1, G2? It's just lambda G1, right? What is the law on sim S? Sim S, what is the law on the symmetric function of a set? What do you do with two bijections? You compose them, right? This is composition. Okay, so rho G1, G2 is lambda G1, G2. I'll prove that lambda G1, G2 is equal to lambda G1 composed with lambda G2. How do you prove that two functions are equal? You apply them to an arbitrary element, and you show that the result is the same. So what is lambda G1, G2 of S? This is G1, G2 star S, right? By definition of lambda G. Where's lambda G? Yeah. Right? Now, by the definition, by the properties or by the definition of a group action, so far so good. Yeah. Well, what is that? This is just lambda G1 applied to lambda G2 of S. Agree? Yeah. Now, what is that? This is just, okay, I'll write here. This is just lambda G1 composed with lambda G2 on S. This is just lambda G1, G2 of S. And here S is arbitrary. So this is let S be an S. Okay, so lambda G1, G2 is just lambda G1 composed with lambda G2, which is just rho of G1 composed with rho of G2. So the product, this function turns the product in G into a product in sim S. So it's homomorphism. Okay? Yeah.
When you say you want us to rederive the result for the,
Yeah.
where should we start? Like, are we starting?
No. Oh. Is it clear here? Is it clear this is homomorphism? Just it turns the product in G. You send an element in G to a function in the symmetric group of S. And this row, G1, G2, will respect. So the product, this row will turn a product in G into a product, or into a law, into the composition in sim S. So this is a homomorphism. Yeah. Yes, exactly. Because star is a group action. Exactly. Wait, here you mean? Yeah, this is because G inverse G is E G star S. And by definition of an action, it's S. Okay.
Don't think G and third G.
Oh, why I put them together? Yeah, because it's an action. Yeah, exactly. Okay. Great. Any more questions on this? Is this clear? Is this homomorphism clear? For example, this is one proof I could ask on it. Show that if S is a G set, then there exists a homomorphism from G to sim S that is not trivial, right? Like it's not send everything to one. That's not necessarily true. Okay, or show that this function is a homomorphism. Okay, I'll not let you, say send everything to one as a homomorphism. I will be sure to be good at these loopholes. Like anybody took a statistics course? Anybody took a statistics course? No, like 324 or 357. Yeah, have you seen sufficient statistic?
324.
Yeah. So once in an exam they ask, find a sufficient statistic. I just put x1 up to xn. Where 10 works. Well, that's right. But that's a silly answer. I think it's yeah, you'll see if you take statistics, you'll see. But this is a trivial. If I tell you find a normal subgroup of G, basically, you tell me one. If I don't specify anything, then that should be correct. But I'll make sure to avoid trivial answers. Okay. Okay, so is this good so far? Yeah. Now what's the kernel of rho? Kernel of rho is the G in G such that lambda G is the identity on S. Okay, what does it mean lambda G to be the identity on S? It means that so G belongs to kernel of rho if and only if lambda G is identity, the identity function on S. If and only if lambda G of S is equal to S for all S and S. Agree? Everybody? Well, what is lambda G of S? G star S is equal to S for all S and S. if and only if what?
It's in the statement.
If and only if G belongs to stab S for all S and S, right? If and only if G belongs to stab S for all. Well, okay, for all S and S, G belongs to stab S. So far, so good. Are we good here? Yeah. Well, if and only if, so if G belongs to stab S for all S and S, if and only if G belongs to the intersection of all the stabilizers. Okay. So far, so good. So far, so good. Yep. Okay. I'll give this here. And let G be a group. So you asked me a question, like when I ask you to rederive this is where I want you to start. Okay? If I ask you to not use the result immediately, to rederive the coset representation, I want you to start here. Okay? Not everything, but I'll tell you how. But I don't want you to rederive everything here. Just this. So let G be a group in H subgroup of G at X. Okay. Then G acts on G mod H, right? How does G act on G mod H? Anyone can help me? So if I take an element G in G and a coset XH in G mod H, where does it go to? GXH, very good. Gx by this and this action induces a homomorphism rho from G to the symmetric group of G mod H, right? Agree or not? My set S is G mod H. Yes or no? Is a set of left coset. This is my set S. This is my G set, G mod H, the set of left cosets. Now, how many left cosets do I have if H has index n? Everyone? N. Label them 1, 2, 3 up to n. Just write them. Label them. And then, well, it's not very formal, but label them 1, 2 up to n. Sim G mod H, what will it be equal to? Sn, right? Is isomorphic to Sn. Agree or not? Just label your elements 1 up to n. Instead of labeling them H, G1H, G2H, and so on, just label them 1 up to n. And sim G mod H is isomorphic to Sn. Of course, you can write a full. Sometimes intuition works well. Okay, you can write a full and prove that if two sets have the same finite cardinality, then their symmetric groups are identical. Okay. But, yeah. Now, what is the kernel of rho? What's kernel? Is what is the kernel of rho? Is the intersection of the stabilizers, right? Now the intersection of the stabilizer is n, let's say. I derived it in class with the stabilized that the kernel is the intersection of XH, XH. Okay? Try to look at the kernel to see how I derive. It's not a bad proof. Proof is like something similar. Yeah, anyways. Okay, this is the kernel. Hence, I mean, here you can use what you need in this question. Oh man,
Low battery.
yeah, battery is low. Close.